Wait 2 seconds. Let me find my headphone. I don't know where it is. Oh, there's a cat cam. Thank you. 2 seconds. Let me fix my headphone. Guys, can you try say something?
Hello.
Okay, that works. Thank you. Uh, next thing is to get OBS. Next thing I should do is this. Okay, and I need my iPad. Okay. 1 second. I still don't have internet though, guys. I still on my 4G. And I need to connect to my phone. And what I need to do is I need to share the screen. Yay. And the shut windows. Okay, great. Okay, that works. Sorry, guys, taking so long. So this is lecture 3. Okay. Today we're gonna learn a little bit more how to get computer to do cool things, which is interpolation and integration. They are actually very, very closely related. Okay. Let's do interpolation first. Let's do interpolation first. Let me try to explain to you what interpolation is trying to do. Okay, here's what it tries to do. If you have some data point, this is some x, and this is some y. And if I give you these 3 data points, okay, so you know the value of the function at exactly 3 points. So this thing is x1, y1, x2, y2, and actually, let me give you a number like 0.5 and 1. And this thing could be 0.5 and, nope, not 0.5, no, 1 and maybe 0.5. And this point could be x is 2 and y would be, I don't know, 0.75, something along that line. Okay, everyone got the idea, right? You have 3 points, and then the question that I'm asking you to do the interpolation is the following. Can you give me the value at this point, right? At x is equal to, I don't know, 0.75, which is about over here. I asked you what the value of the function, right? So these three are sample for some function. Okay. What would you do? What would you do? Right? We have 3 points, right? I say that this function, when you plug in 0.5, it gives you 1. If you plug in 1, it gives you 0.5. If you plug in 2, it gives you 0.75. And then I ask you the question, what if I plug in the value of x equals 0.75? What would be the value? What would be your guess? What would be your guess? What would you do? What would you do? You can describe it qualitatively as well. What would you do? Okay, this is what's called interpolation, because you know that 0.75, right, is between 0.5 and 1 is between these two x's, which we know the value. So we should be able to guess the value in between. Whether the guess is right or not, that depends. But can you give me some basic guessing method that you would do? Anyone? I know you guys ate already. You guys should have power, or maybe you ate too much. Average is not bad, right? Average is not bad. Dan, I'm going to guess the following. Okay, I'm going to guess the following. So Justin and Adil suggest, Dan, 0.75 is exactly halfway between 0.1 and 0.75. So maybe I'll just do the following, which in fact, this is what you're doing. This is what you're doing. You are saying, okay, Ajahn, this is my guess for the function. It's a straight line, right? Which I'm pretty sure by now you know how to find a straight line function, right? Right, you can find m and c and whatnot. We do something more fancy like last 2 times. Okay, and then okay, we can guess with a straight line. Nothing is wrong with that, which is actually always my first answer. If I have a lot of points, then everything is a straight line. If I have a lot of points, right? If your points are like this, right? Then I'm gonna guess this. That would work, right? That my function is just a linear piecewise function. Okay, between all the points. Okay, that works, except we can do something better. That's exactly what Tanawin was saying, right? Okay, Ajahn, this actually looks like quadratic function, right? This actually looks like quadratic function. What if you use, let me pick the color. Okay, green. What if we use the fact that there's another point here? Okay, which means you can draw maybe a parabola, right? That pass through all the point, right? This is a parabola, which we don't know the function yet. We can figure out later, right? Parabola that pass through all the point. Okay, that would be the second guess, and you think, okay, you may think actually it's not better, but it's just another way to do it. You're gonna learn that in machine learning later. That it's actually not a better way, not strictly better way, but it looks better, right? Okay, we use more information. We hope it's better. Okay, everyone sees the idea, right? That actually you can use more point, and then you get a more complicated function that pass through all the point. And then I ask you, what is the function at 0.75? Okay, you just look at the green line, which is clear that the green line and the blue line is going to have something different, right? Going to be a little bit different. It's not going to be exactly the same. Okay, but both of them try to solve exactly the same question of interpolation, right? That means guessing the value in between the point that you know what the value of the functions are. Okay, so far so good. So now let me go back to Tanawin's question. right? Hanawin question suggests that, okay, that is quadratic. So the question is it really quadratic? Okay, let's look at this. Let's look at this. Okay, so if you write a quadratic equation, what does it look like? Can you tell me? What does it look like? A quadratic equation. Can you give me a general form for quadratic equation? Anyone? Or Tanawin? What exactly do you mean by quadratic equation? Good. Ax squared plus bx plus c, right? Actually, let me give you the linear one. It looks y is mx plus c, right? Or let me just write ax plus b. Okay, and then we say, okay, quadratic y is ax squared plus bx plus c. So let me ask you, for linear one, how many unknowns? How many unknowns? No, not one. How many unknowns that you need to solve to fully specify the line? Right, it's two. There are two, right? There are two. So which means if you have 2 points, you have 2 equations, you can solve exactly what A and B's are. Okay, right? This is very important point, which means there are 2 coefficients, right? Or 2 unknowns. You only need 2 points to solve for it, right? By definition, two unknowns. You only need 2 points to do it. You need 2 equations to solve 2 unknowns, right? But quadratic, right? You have 3 unknowns, right? A, B, and C. So how many equations would you need to solve exactly from A, B, and C? In general, that there are like degenerate case and so on. But how many equations do you need to solve for all 3? How many equations would you need to solve for 3 unknowns? 3, right? So as in general, to solve n unknowns, you need n equations. Okay, so this thing is called degree 2. Degree 2 polynomial. Because of that too, the highest power of x is 2. So if you have 3 points, degree 2 polynomial is good enough. Okay, but I think you see that if you have 10 points, how many degree would you need? Any guess? If you have 10 data points, right? If you have it here, there, 4, 5, 6, 7, 8, 9, 10. Yes, you would need nine polynomial of degree 9, right? Okay, and I think if I try to ask you to solve for the 3 unknown, then okay, you start getting upset with me. If we ask you 4, then you get really mad at me. But if I ask you to solve 10 equations at the same time, then you gave up already. So we're not going to do that, right? We're not going to do it by solving that. But the idea that I want to give you is that if you have this, you can draw the polynomial that passes through every single point. Okay, exactly every single point. You can find a polynomial that passes through every single point. And the goal of the first half of today is to find exactly what that polynomial is without having to solve the equation. Okay, we're going to be a little bit smarter. You can solve the linear equation, which we're going to learn how to solve next time, but we can do something smarter as well. Is that clear on what we're trying to do? Right? We are trying to find the polynomial that passes through every single point. Okay, it has to pass through every single point, and that gives you all the interpolation, all the value of the function in between. Are we good? Okay. So let's think about this. This problem can be hard, can be easy. The guy who figured it out, name is Lagrange. Wait, Lagrange, not Lagrange. Someone complained to me. I think the lecture not say Lagrange, but his name is Lagrange. 2 different person. They are both really, really smart. They are both really, really smart. Okay, so let's look at our problem. Our problem, right? We have 9 data points. We have n data points. Let's call n data points. Actually, let's make it 4. What did my lecture note say? 4 or 5? Because I'm too lazy to write. Let's make it 4 points. You have 4 points, right? 4 points, which I'm gonna call it actually, if I make it abstract, then you're not gonna see how it works. Let me make it less abstract. So let me make it 0, not 0. Let's make it 1, and y is 2. Let me make it 2, and y is, I don't know, 1.5, and then 3, and then y is 3, and then 4. This is the value for x, and this is the value for y. Actually, let me make it 4.5 as well. It doesn't have to be regular. And this thing may be 0. I don't like 0. Let's make it 1. Yeah, so far so good. If you try to plot this, I'm sure you can plot this, right? 1 is 1, 2. And then 2 is 1.5 is around here. 3 is 3. 1, 2, 3. And 4 is 1. So this is what it looks like. This is x and this is y, right? When it's 1, 2, 3. Oh, actually move a little bit. 4, and this is about 4.5. So your function, your point looks like this. And what we are trying to do is we are trying to find a polynomial of degree 5, right? Degree 3. Degree 3 that pass through all the points. Okay. You may think that this is kind of advanced. This is like useless. No, actually, this is like everything in machine learning. Everything in machine learning, all the cool stuff that you see are actually interpolation, right? So for example, let me give you a very general, vague idea of what machine learning is trying to do. You've seen a dog, you've seen another dog. In between, there are a lot of dogs, right? So you want to say that, okay, the picture in between is also a dog. That's what you're doing. You are interpolating between the two pictures and so on. Okay. So all the machine learning is trying to do is called interpolation, and its success is in a various degree. It's of a various degree. Okay, which I think we're gonna open it next term, or maybe next term. I don't know. Should be next term. Okay, so remember our goal is to do Lagrange interpolation to find this polynomial. Anyone has a good idea though? Anyone has a good idea? What would you do? What would you do? Make sure whatever you do extend to like degree 10 as well. If you think about this problem is hard, right? You can do like what I suggest earlier by solving like 4 equations, 4 unknowns, and so on. But we want to be smarter. And typically, to be smarter, you simplify the problem a little bit. If you take class with me yesterday, right? You change the problem just a little bit, and then you're gonna combine it. Okay, so let me change the problem a little bit. Let me make it something easier. Okay, instead of all these random values, right? The y is random value. Okay, so I'm gonna ask you the following question. Can you give me a polynomial that is 0, 0 at 1, x equal to 1, x equal to 2, and x equal to 3? Can you give me a polynomial that is 0 at these 3 points? Yeah, right. Remember, I picked only the first 3. The fourth one is going to be non-zero. You can actually prove it, but can you give me a polynomial, some sort of polynomial that guarantee to be 0 at x equal to 1, x equal to 2, and x equal to 3? Can you give me something trivial? A polynomial that is 0 at x equal to 1, x equal to 2, and x equal to 3. What is it? Y is equal to what? Let me call that W of x. Anyone has a good guess? Actually, that's the correct answer, except that let's try all what I'm trying to say. Yes, if this is 0, then yes, it's 0 at every point. Okay, make sure also that not 0, any value, not 0, at x equal to 4.5. I like to answer though, with a no. Okay, so your function should look something like this, right? This is x equal to 4.5. Your function should look something like this. Has to be 0 here, 0 there, 0 there, and maybe negative something over here. That works too. Anyone? Something better than 0. 0 is a good answer, except it's not what it's not quite what I want, because we have no way of manipulating it. Anyone has a good idea? Anyone has a good idea? A polynomial that is 0 at 1, 2, and 3, but not at 4.5. You learn something from math, right? From high school math. Sine? No, not exactly sine. No, not sine. A polynomial. Sine is not exactly polynomial. We learned that from Taylor series, right? Not exactly polynomial. You need like infinite number of degree. Something much simpler. Something much simpler. Something much simpler. Okay, let's start with something even easier. What if I want a polynomial that is 0 at x equal to 1? Y equal to what? If it has to be 0 at x equal to 1. X minus 1. Good. X minus 1. What if I want it to be 0 at 1 and 2? Give me something simple. 1 and 2. Not just 1 anymore. Let me give you a hint, and this is the hint. Good, right? If you do this, x minus 1 and x minus 2, then when you plug in x equal to 1, then the first guy is 0. Then you plug in 2, the second guy is 0. So when you multiply, it's going to be 0. Right? Everyone's clear on this, right? This is a neat trick, right? Which means, now, give me this. I want it to be 0 at 1, 2, and 3. What kind of polynomial is that? Very good. X minus 1, x minus 2, and x minus 3. Right? So far, so good? Okay, so it's clear that it's going to be 0 at 1, 2, and 3. But at 4.5, it's clear that it's not going to be 0, right? At 4.5, let me show you. At 4.5, you have 3.5 multiplied by 2.5 multiplied by 1.5, right? That's good. Okay, everyone good with this? Let me call this function W4.5, which I'm going to fix it later. I'm going to make it a little bit cooler. Okay, everyone with me so far? Now we have a function that is 0 at 1, 2, and 3, but not at 4.5. And more than that, this thing is of degree what? What degree is this? What is the highest power of x? What is the degree of this guy? Degree is the highest power of x when you expand it. It's degree 3. Exactly what we need, right? Exactly what we need. Okay, now let's do something cooler. Let's do something cooler and a bit harder. So now at 4.5, I don't know what this value is. It's, I don't know, 6, 7, 8, I don't know, maybe 9 point something. I don't know what that number is. Let me make it harder, right? We did not specify what the value at 4.5 should be. What if I specify the value at 4.5 that it should be 1? right? So not only that it has to be 0 at these 3 points, at 4.5, it has to be exactly 1. I need space. It has to be 1. How should I fix this, right? It was some other value at 4.5. Okay, this guy was some other value at 4.5. If I want it to be 1, what should I do? Right, I want a polynomial that is 0. And yes, we're gonna fix the function, Adil. The function have to be 0 at 1, 2, and 3. But at 4.5, so 0 at 1, 2, and 3. But it has to be 1 at 4.5. This is close. What we had here is really close, right? It solved this guy. It's 0 at 1, 2, and 3. But at 4.5, it happens to be, I don't know, 9 point something. What would you do? What would you do? Take away 8.xx is 8, right? Okay, let me make it 8. What do you mean by taking away? Minus 8.xx? How is it 0 at 1, 2, and 3? Okay, that's easy, right? When you plug in x equal to 1, the first parenthesis, the first term becomes 0. So whatever the second and the third term give you, you don't care. It's going to become 0, right? When x is 2, the second term is going to become 0. So you don't care what the first and the second and the third is. And when x equal to 3, the third term becomes 0. So when you multiply it with all the other things, it becomes 0. Are we good, Manit? Okay, good. Adil suggests the following. Adil suggests something very close. So let's look at what Adil suggests. Okay, so Adil suggests minus 8.5. That's easy. Whatever that value 8.8x is, that has one very important problem, one very serious problem. That when x is 1, yes, the first term becomes 0, right? The first term becomes 0, but not anymore. Now when x equal to 1, w gonna give you minus 8.5 instead. Right? So subtract is a bad idea. But Van is suggesting something else. Van is suggesting, okay, Adan, because subtraction will give you a problem because it gives you some offset when it is 0. But I know that when 0 divided by any number is 0. So if I divide by any number, right, it's not going to screw up on my solution over here. By dividing by some constant, right, it's not going to screw up my number. And if I were to be smart, here's what I'm going to do. Because I want it to be 1 at 4.5, right? So I'm going to make sure that I cancel all these. Specifically, what that means that, okay, I'm going to divide by 4.5 minus 1, 4.5 minus 2, and 4.5 minus 3. Okay? Okay, now you can see how that works, right? So it doesn't change, right? When x is 1, the top part is 0. When x is 2, the top part is 0. When x is 3, the top part is still 0. So that's good. Now, what happens when x is equal to 4.5? Right? When x is equal to 4.5, the top part over here, this guy, gonna become, right? The top part, I plug in x equal to 4.5, 4.5 minus 1, 4.5 minus 2, 4.5 minus 3, right? And then divide by that exact same thing. Then I guarantee that should be 1, right? Right? Everything cancel out and it should work out to be exactly 1. And it is what I need. Let me change the problem a little bit to make it a little bit cooler. Sorry about that. Let me change this to 1.5. So you see something. 2 seconds. Let me change it to 1.5. Okay. Okay. Let me change the problem a little bit because I want to illustrate one point. Okay, great. Everyone is with me so far, right? That W4.5 now give you exactly 1. Okay, this function W, which you know how to construct, right? It has to be 0 at all the other points. Okay, and it's going to be 1 at exactly 4.5. Any questions so far though? Any questions so far? If you don't get this, you're going to be lost for the rest of lecture. That this polynomial that you just constructed has two very important properties, right? It is 0 at all the other points, but at the point you want, 4.5, the value is exactly 1. Any questions so far though? Any questions so far? Like how does this even work? We're gonna assemble things together. It's gonna become very magical to you when we put things together. Any questions? Okay. If not, let's make the problem a little bit harder. Let's make the problem a little bit harder. Okay. What we want is not exactly 1 at 4.5, right? That's why I changed it. What we want is 1.5 at 4.5. What kind of polynomial does this? Instead of 1, I don't want 1. I want 1.5. Right? So that means this is what I want. I want the function to be 1.5 at 4.5. What would you do? How would you fix it? What we have already is really close, right? What we had already is really close. How do I fix it? Any good idea? Good, just multiply by 1.5, right? Good, that's why I asked you to do 1. So all you need to do is make sure this guy is here, and then this is equal sign, and then multiply that one by 1.5. Aha, right? This looks really cool because now you can construct it to be any value you want, right? So far so good. So far so good, right? So we have a polynomial that is correct exactly at 1 point. Not bad, not bad, right? What we have over here is correct. Is what we need, except at 1 point. Except it's only correct at 1 point. So far so good. And by this extension, okay, by this extension, it means you can construct this function. You can construct this function at all the other points as well. At all the other points, and let us do that real quick. Let us do that real quick. Make sure you understand though, because you're gonna need to teach computer how to do this. Okay. So at 1 and 2, the function that does that, let me call that W1. W1. W1 is going to be, let me leave out the 2. It's going to be quite clear, right? You want it to be 0 at 2, 3, and 4.5. Oops. And you divide that by 1 minus 2, 1 minus 3, 1 minus 4.5. Okay, and you know, in the back of your mind, you can make it 2 if you like. You can make it 2 by just doing 2W1x. Okay, but I'm not gonna write it here because it's gonna mess up all the other nice thing. Okay, let me complete that. Complete this. Second. And W2. Okay. So let me recap real quick because if money is lost, like 10 other people are gonna be lost as well. So our goal right now is to make a function that is 0 at all the other points. Right. Follow me first. We are making a function that is correct at exactly 1 point for each point, and then we're gonna combine them later. Okay. So this W that we construct, right? I think you can verify yourself. It is 0 at 2, 3, and 4.5, but it's 1 at 1. Okay, W has that property because how we construct it. This is going to be W minus 3, oops, W minus 1, W minus 3, W minus 4.5, divided by 2 minus 1, 2 minus 3, and 2 minus 4.5. And let me write this real quick. Not WX. Divide by 3 minus 1, 3 minus 2, 3 minus 4.5. Okay, right, exactly what Saran was just saying, that what I'm making, each of these function is like correct at exactly 1 point. But our real goal is to make the function that is correct at every single point. Okay, I'm pretty sure some of you see it now. What should we do? If I want the function, actually it's a yes answer, but you need to know how to combine it first. Now, okay, so this function is correct at exactly 1 point at 4.5. This function is correct at 3. This function correct at x equal to 2. This function correct at x equal to 1. How do we combine them? I want a function that is correct at 4 points. What would you do? What would you do? Right? All these functions multiply. No, you don't want to multiply. What is the other choice? Add. Let's look at what happened when you add them. Let's look at what happens when you add them. Okay, so let's take 2W1 plus 1.5 W2. Okay, let's look at this first before we add the 4 terms. Okay. Okay, before we do the 4 terms, let's look at this polynomial. Let's look at this polynomial. Y is 2W1x plus 1.5 W2x. Okay, let's look at this function. When you add them, what happens? Can you tell me what is the value of the function? What is y when x is 3? That y. And y is that as well. Y when x equal to 3. What is the value? It's gonna be 0, right? Very good. Because W1 at 3, that's guaranteed to be 0. W2 at 3, that's guaranteed to be 0. Now you see, right? There's some magic going on. What is the value of y of 1? What is it? It's exactly 2, right? Because y of 1 is guaranteed that this guy is going to be 1, this guy is going to be 0, right? So y of 1 attain the correct value. This is the correct value that we want. Not only that, you can try y of 2. What does it give you? Y of 2 is what? It's 1.5, right? Because y of 2, this W1 at 2 is 0, right? W2 at 2 is 1. So you're going to get exactly 1.5, which is correct. We good? So the reason that I want the reason that I want W to be 0 at all the other points is so that when you add them up, they do not interfere with each other. Someone with me though. This is very clever. Right. You can write if with multiply. How is W2 equals to 1? Good question. Because the way we construct it, think about this. W2 construct like this, right? Because we know when W2 is 2 of 2, right? When x equal to 2, when x equal to 2, the top part is going to be 2 minus 1, 2 minus 3, and 2 minus 4.5. And the bottom part is exactly whatever you have on the top, right? So they're going to cancel it to 1. And that's by construction. Are we good? The others run. You see, right? This looks like magic by construction, which means now you get it that if you want the value of the function that's correct 4 points, what would you do? You just add 4 terms, right? This is the idea of decomposition, right? If you decompose your problem into something that do not interfere with each other when you add them up, then you can solve the little piece one by one easily. This is the idea of decomposition. The idea is actually very closely related to Fourier series, which is your homework. This homework. Speaking of homework, why don't you guys hand in the homework? There are so few people handing the homework. Please do it. Or else I will start setting the deadline. Do it. Okay, so I think everyone got it, right? That if you want it to be correct at 4 points, okay, that's easy. I just do y is equal to whatever the value I want at y, which is 2w1 x plus 1.5 w2x plus 3 times w3 of x plus 1.5 times w4.5 of x. And then the value is going to be exactly correct at every single point you need, which is our polynomial, which is that polynomial that we want at the beginning. Right? So this polynomial does exactly the job you need. And I don't know, I think it's very clever. It doesn't require like really complicated math, but I think once you see it, you know it works right away. Okay, and this guy has a name. It's called Lagrange interpolation polynomial. Lagrange. You know Lagrange, right? Lagrange is like smart guy. Especially risky, you should know Lagrange. That Lagrangian is from Lagrange. Interpolation polynomial. It's one of the, it's a clever trick. It's a really, really clever trick. Once I tell you, now you think it's trivial, right? The W is actually to make sure that they do not interfere with each other. The W is to make sure that that 2 will never interfere with that 1.5 because because it's gonna be 0 at whenever you need it to be 1.5. Right? This is the idea of decomposition. You want to decompose the problem into pieces that they do not interfere with each other. So you can solve the problem one by one and then put together, and then everything don't break when you put things together. Yeah, I think it's really clever. The first time I heard about it, it's like, oh, come on, this way is really, really clever. There are other ways though. There are other ways. But this way, I think is very clever. It shows like how you think about it very clearly. Of course, you can brute force doing the solving for linear equations as well, which we're gonna do next time. But this thing is clever. Okay, any questions so far though? Any question? We're gonna teach computer how to do this. Because if you have 100 points, you're not gonna do it by hands. Any questions though? Any questions? So the goal here is we are going to programmatically construct these functions. programmatically construct these W. It may have like one of the worst big O ever. I don't care. Okay, as long as you get it to work, then you learn higher order function. You need to learn how to do higher order function, the function that split out a function. Anyone? Any question though? Any question before we get it to teach the computer how it works? Any question? Like how we construct the W's, how we put together all the W's and so on. Yes, what's the question, Manit? If you have nickname you want me to call you, that's just tell me. How we construct W. Okay. Let me repeat again. Okay. So remember the way we construct W, there's only like one simple requirement that W1 has to be 0 at all the other point at 2, 3, and 4.5, which means all the other x's. Okay. And the other requirement is that it has to be 1 at the value we want. Right. That is the only requirement. Okay. So the way we should think about it is that, okay, now I know how to get it to be 0 at 2, 3, and 4.5. That is easy. You just multiply by x minus that number, right? You just multiply together x minus all the other points, because when x is 3, the second guy is going to be 0. You multiply by whatever you want, it's going to become 0 anyway. Okay, so the first problem is solved. Okay, the first problem solved, that is 0 at 2, 3, and 4.5. Okay, the second problem, that is we want it to be 1 at 1, but if we only have the top part, right? We only have the top part, then when it's 1, when x is 1, then the top part is going to be a whole bunch of chunk multiplied together, which is not 1. Right? It's going to be 1 minus 2 times 1 minus 3 times 1 minus 4.5. So the trick that Rand suggests is just to divide whatever you get at 1. Right? And then the top part and the bottom part are going to be identical, and they're going to cancel out and give you exactly 1. So that's how we construct W. Is that clear, Manit? Okay. But what we're going to do next is that we might have like 7 points, 10 points, 100 points. It should not matter. We're going to teach computer how to do it. Okay. And also, you notice I don't even bother expanding this. I don't even bother expanding this. Okay. And you can see that this thing is degree 3. Right? Because each one of them is like x cubed. Right? Each one of them is x cubed. So the degree is still degree 3. Exactly what you need. Okay, so if there is no other question, then let's go to our notebook, which I haven't loaded. Let me load it real quick. Or maybe I have it already. I don't know. What's up, Saran? How are we going to automate that? Yes, you're gonna see. You're gonna see. I'm gonna teach you like the basic, and then you're gonna fill out the rest. What's up, Saran? The other Saran. You guys have nicknames, so why did we choose 4.5? What do you mean? Because we want it to be 1.5 at 4.5. And you asked me why is it not 4? Because if I show you 4, you thought that it like normal grid, the spacing is regular. That's why I choose 4.5, for you to see that the spacing doesn't have to be regular. Right? The x and y that you are given, this could be 1 and 2. Right? This thing could be, I don't know, 99 and 10, doesn't matter. It doesn't have to be 1, 2, 3, 4. It could be any numbers. Okay, that's why I use 4.5. So you don't see it as regular grid. How are we going to automate that? That's a good question, which is what you're gonna need to figure out, but I'm gonna give you some hints. But let me get my notebook first. Okay. I don't know about you guys. I think the first time I see this, like, oh my God, this guy named Lagrange is so smart. I'm not even sure who came up with this, The polynomial is called Lagrange, but this method might come like 10 years afterward. So typically the sign, if the field, any field that is underdeveloped, okay, that means is within the phase of like rapid development, all the formula, all the proof are gonna look really, really messy. But all the things you see in the textbook, they are mature. They're mature enough to put in a textbook. So all the formula you see looks really nice. All the formula you see looks really nice. All the proof you see looks really simple. Way back then, no, it's totally different language. If you took discrete math with me, you saw that proof, right? That proof of Pythagoras. The first time Pythagoras did it, doesn't look anything like that. It's much more convoluted. It's correct though, but it's much more convoluted. Okay, so let's go to exercise 3. Okay, my neck is gonna kill me in a second if I keep doing this. Full screen, thank you. There. And I need my terminal. Oh, that's not my mouse. I need my canvas. Okay, if it's fun, don't forget to do the homework, Sharon. Don't forget to do the homework, whatever you do. It's very important. Exercise 3, right? 3. What is this? Confirm complete testing. What? I have two-factor already. It's not happy. Copy. You guys should do two-factor authentication. It's a really smart idea. I thought about it like 10 or 20 years ago, that we should do this. Except 10 or 20 years ago, you don't have iPhone. Which two-factor gonna give you more trouble than what it was. But right now, the technology is ubiquitous enough that two-factor is a good idea. Git clone. By now, I think everyone has Jupyter Notebook on your computer, right? In some shape or form. Unless you really like Colab, then I have no argument with you. Interpolation and integration. Okay, there, that's our notebook. Let me get this thing out of the way. Oh, I only have 4. That's not even fun. Okay, so let's do this together. Let's do this together. Let me teach you something really cool. Okay. For those of you who learn functional programming or whatever it's called now, maybe parallel programming style or something. For those of you who learn functional programming already, this is just a revise on how you do it in Python. Okay, so typically here's what you do, right? Remember, we need to generate W. So we need W generator. But if you think about it, W is a function. W is not the W is not a value. It's not real. It's not like 5. It's not like 10. It's not an object, right? It's not an object that holds like 10 properties. It's a function that when you pass in a value and it should work. Okay, so you may ask, okay, Ajahn, how would I construct a function? How would I return a function? Yes, you can return a function. Okay, let me show you. Let me show you. It works in, I don't know, in Python for sure, in Scala for sure, in JavaScript for sure, but Java, I'm not sure. Although all the modern language has it. Let's call adder. Let me show you something. Adder, and then you put in, let's call this C. And you want to return a function that takes in a value. Okay, now that's a mind blown, right? You do something in programming one. In Java, you can replicate this somewhat by using interfaces. You can replicate this somewhat. Okay, when you see this code, think about this. Think about this. This is what it does. You take in a value, you construct a function based on a value. The technical word is called closure. If you write JavaScript enough, this is what you're going to see. The technical term is called closure. But let's think about it as a function that you take an argument, it returns another function. So for example, if I say that, okay, f is adder of 3, and then I ask you what is type of f, it's going to be a function, right? Okay. Not only that, it's a function that when I call it with some number, I call it with 1, right? It's going to give me x plus that x, the 1 plus 3, right? It's going to give me 4. Does that sound good, right? You can see how we would generate a function, right? Or you can do this. You can also do this. Adder and I don't know, 10. This thing add 10 to any number. So g of 100 going to give you 110. Right? So you can think about this as like a function factory. Okay? This thing has many names. Oops, this thing has many names. If you want to be a really good programmer, this is some technique that you want to do. So this is, you can think about this as like the program that write the program for you. This is called, has many names, it's called higher order function. Right? Or sometimes it's called functor. Okay. Or if you want to be like more pedantic, it's called function that return function. Right? Any questions though? Any question? You will need this to construct W. Any question though? Any question? This is the simplest example I can give you. To make sure that you understand that Python is actually a very dynamic language. You can return function if you like. You can actually return class if you like. But this is just returns a function. Any questions so far, or any questions so far on like how this thing works? I want you to sort of understand how this thing works. Any questions, or this thing is like very trivial for you guys? Okay, no question. Everything is good. Everything is good. Everything is good. So you forgot about that. What do you mean? You learn about that and then you forgot, right? Okay. You probably learn it in functional programming and whatnot. Okay. 101. Oh, you learn how to return a function. Who taught you that? Ajahn Som or Ajahn Kanat or Ajahn Sansar? I never thought it's in the curriculum because it looks so confusing. Function that returns a function. Okay, so here's what I want to do. Here's what I want you to do. Implement this for me. W generator. Right. The W generator should take 2 numbers, right? The value should be 1 here, right? So let's call that I and others. Let's call that X. Don't call it X, call it I. I is bad. Let's call it 0. Let's call it anchor. So this thing should return W such that W anchor is 1 and W X is 0 for all X in others. That's it. So Please do this for me. Please do this for me. Okay, once you have this, your life going to be much easier. But if you don't have this, your life going to be so hard. So this anchor is a float, and this thing is a list of float. So from typing list. And let me push the code for you. Wait, what? Doesn't copy for me. Why? Copy and paste. There. Okay, do this for me. Do this for me. Yes, it should be another function which you returns. Just something very similar to the thing on the top. Actually, when you write a function, right, it should be a verb. Let me change it to generate W. Something like make header. Okay, that's a better word. Function name should in general be a verb. Okay, do it, and then you're gonna be so proud. Something very similar to the top part. So you should yes, W X, and then you should return W. But that dot is depends on how you write it. Should be a bit long. What is the input of other list of float? So for all the other points that you don't want, you want it to be 0. So it's a list of float. So if you got it, raise your hand so I know that you got it. Test two. I think it's very easy to test, right? Should be about 3 to 4 lines. If you're done, raise your hand. Right, this is your test. So W is generate W and 1. I think I can do this. The correct way is to do this. Yes. Oh, NP. Wait. Blah, 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 math.truck. Okay, or np.truck works too. Do math. Yeah, 3 lines. Oops. This is what you do, you know. Do NP dot product. It's like sum, except it's a product. I'm pretty sure there's a native Python product somewhere, which I don't remember what it's called, but this is close enough. Which line, 7 or 8? So it takes X from here, and I say that give me the list of X minus the value of O for all O in the others. So you can do this. So for example, you can print it out if you want. So it's like, give me the list of X minus all that. And then take the product. So we can do that. Learn for comprehension, right? We learned for comprehension for many times already. We did many for comprehension. It makes your life 10 times easier. Okay, this is another thing that you should learn from this class to pick up like how to write proper Python. Because I know the only place you learn Python was programming one, right? So this is probably the second class you use Python. So you're gonna pick up on how to write a more proper Python, like using all the weird features Python has. Python is very feature rich, except it's like the slowest language there is. It saves developer time, but it doesn't save runtime at all. Which if we have time, we might cover how to make Python 1,000 times faster. And the answer is to write C in the background. If we have time, if we have time. Okay, if you're done, raise your hand. If you're done, raise your hand so I know that you're done. I know some of you are gonna try it yourself, so you are more than welcome to try it yourself. If you're done, please raise your hand so I know you're done. If you want to try it yourself, and try it. This is where you learn the most actually. Okay, so for those of you who are done, use this to fit all these points and make sure that it works. Okay, for those of you who are done, use this that you just made to fit all these points. Get the function that fit all these points and draw the line that we drew earlier. Oh, actually, just just write a function that you can put in any sort of. So let me give you a signature. So it should be make Lagrange. Actually, called Lagrange, and you can put in all the x's and y's. So let me make a list of float. And the way you use it, you can read something like that. Yeah, for those of you who are done, do this. Let me push this. Okay, for those of you who don't make this function, it should be really short as well. It should be like ridiculously short. So this is the part that typically when you guys are in actual class, once someone is done, you're gonna turn your left and teach your friends, but I'm not sure how to do that online though. So if you're struggling, just ask. Just ask. Or you guys might have like private chat channel, private Discord or whatnot. You can do that as well. I don't mind. Okay. Make sure that you learn. I don't want anything else from you except the fact that you should learn the subject. Oh, because that's how you compare it to one. Okay, so let me go back. Wait a second. Good question. Because you want to say this, right? You definitely want to say that, and it may work. You want to say this. W1 should be 1. Except it's a float, right? So you cannot compare it directly like this. So you have to make sure that, okay, it's close enough to 1. That's why I do this. Okay. While the other ones, I really want to say this. I really want to say W2 is exactly 0, except it's a float comparison, which you learn in programming 1, right? It depends on the representation and whatnot. So instead of that, I need to say this, ABS, absolute of W2 minus the value I want is less than 1 e to minus 7, but minus 0 is like meaningless. That's why I take it away. What is the anchor? Anchor is the point where you want it to be 1. Okay. Others are the point where you want it to be 0. Or if you want to be cool, you can do this as well. Except it's gonna make your life like much harder. You can do this. That works too. That works too. Except you're gonna get so confused. Why are there 2 parentheses? But if you think about it, that's how it works, right? Because this guy returned a function. This guy returned a function, which is take in another argument, and it give me a number. Okay. Some people call this, another name for this is called partial. Another name called partial. So it looks like a function, but it's not completed yet. Which reminds me, there is that old flow on some Python list, I think. There's a topic called Python hidden feature or something. Let me see. Hidden features of Python. Yeah, this is something you should read this evening. This evening. There is a lot of weird things, like funny things you can do with Python. Like, so for example, it's the only language I know that you can do this. Chaining the comparison is the only language, even by now. Scala or Rust doesn't do this. It's the only language I know that can do this. What should we write in Lagrange? Good. You should write the function. Okay, so let me see. Let me specify it better. Okay, it should give you return Lagrange x such that Lagrange x is y for x and y in SIP xs and ys. That's not good, isn't it? Right? That means it come in a pair, right? So that means Lagrange 1 should give you 2, Lagrange 2 should give you 0, Lagrange 3 should give you 2, and Lagrange 7 should give you 1. And all the other points, then you don't really care. Except you need to be able to give Lagrange 1.5 as well. Are we good, Vishnu? If you have time, read this. Then you're going to see a lot of weird things Python can do. Look at the thread. It's 13 years ago. How old are you guys? You guys are like 17, 18, 19, 20, right? So this is asked 13 years ago. Way back then, Stack Overflow is an easy paylace. That is why Ajahn Roy and I have a really high score on this. You know Ajahn Boy, right? You gotta take class with him sometime. Ajahn Boy and I have like so many score on this one. I don't know, where is it? There. Ajahn Boy is like 10K. I don't know. Way back then, it was all easy question. Okay, once you have this, please plot it and make sure that it passed through all the planes. This is what you should do. Do this. I can do this in one line, but let's not do it. Just right. Just need this. Check something real quick. Let's go the big. Oh, let's call it. This is easier to read. And that's it. Yeah, this is what you should get. Make it a little bit longer. Yeah, you see, I can actually lump this thing up into one line, but it's going to be so hard to read. I push the code, and if you're done, let me know. If you get this graph, let me know. I want you to try to yourself, and also read my code afterwards, so you see like how to make it like really compact and readable. Right? We're not trying to write the most compact code, but you're trying to write the most readable code. Okay. If you're done, please raise your hand. You should get this one. You can see this is a polynomial that passed through other point, exactly what we need. Oh, okay. That's Okay, raise your hand if you have this graph already. Just use the W generator, the generate W that you made. Make your life a lot easier. So in this class, the code is typically really short, except you need to think before you do. You can make it really long too, if you don't know what to do. Anyone got it? No one raised the hand, so I'm not sure. If you are lost somewhere somehow, are you guys working on it or what? I push out the code to the branch, the usual branch. You can see the code there as well. It should, right? It should, because you need W's in Lagrange. And that's why I don't put them like together. That's why I do not put them together as well. You can actually put everything in one function, but just don't. It's so much harder to read. So I think this is gonna take some time for you to get used to the fact that function is something you can return. So it is really a shorthand for interfaces in Java. It's really just that. But that would take you a while to figure out that it really is interface. You can do the same thing with interface. Okay, you should get this right. You get the idea. We have the polynomial that pass through all the point. Like if I ask you what is the value at, I don't know, 2.5, the value at 2.5, you can do that as well. Give you the value at 2.5, which is 6 something, not bad. Okay. Please raise your hand when you are done, because I need to teach you something else too. Another thing. Please raise your hand when you are done. Also, in fact, this thing, if you go read the lecture note, inside it's actually Taylor series. But you're doing something smart with the Taylor series to get this. Okay. There is a Taylor series working behind this as well. The lecture note gives you like way more details than you would ever need. Okay. So stick with the exercise and the homework. That's actually what I want you to learn. Okay. So the rest you're trying, right? Or you gave up already? I give you until I give you 5 more minutes. I give you 5 more minutes because I want to teach you something else. The lecture is very mathematical. Make sure you can do the homework and the exercise, then I'm happy. Okay. Some proof in the lecture note is it's just for the completeness. Okay. Not many people are gonna need to use that, but you're gonna need to use. A lot of you are gonna need to use what you did in the homework for like real life. Right? If you can formulate the problem, that's like 21st century skill, even 22nd. As long as you can formulate the problem such that your computer can solve it for you, then you're good. Right? Right now, you cannot ask Wolfram Alpha yet, like how many mangoes I should buy or whatever, apple or mangoes, I don't remember. Whatever the fruit is, you cannot just ask Wolfram Alpha that question and then they're gonna figure it out for you. You need to understand the question, the mechanics behind the question, then put it in. So that's very good skill for you to have. Translate the problem into something you can throw at a computer. Yeah, but not about proving the convergence. Those are not something I'm going to ask you. Okay, it's good to know, but not something that is necessarily for your skill, just for your curiosity. Like, how do we know? That being said, please do the homework. I beg you, or else I'm going to start putting out the deadline. There are also random Indian guy on YouTube that could help you as well. But they help you with the technique, so they don't help you with the formulation. The formulation is something you kind of need to learn yourself. Okay, so let's continue. I want to point you out with some weakness, or maybe you can think about as a strength or a weakness. It's actually a weakness of the interpolation that looks like this. Okay, so here is an experiment that I'm going to show you. You don't need to type it on your own. I'm going to show you the following. That okay, let's say you have a sine function for 0 to 2 pi, which is like 11 point. I take 11 points from it, and then I try to do the Lagrange polynomial. Okay. Dot what? I call Lagrange. It's made Lagrange, not Lagrange. Lagrange. XS and YS. Okay. So I make that function, and now I'm gonna plot it to see what it does. Is 0 and 2 times pi and 100. So you see the lines. Plot. Okay. So I made the Lagrange polynomial. Oops, Lagrange polynomial. And we do this, and it looks like a psi function, right? It looks like a psi function, very, very good, like a psi function. Okay, I can even compare it to the real thing, right? So I can compare it to a real thing. And let's make it, I don't know, red. Okay. So you can see that it's really, it looks like a psi function, which is good, which is good. Our interpolation and our real function that we're sampling from are almost exactly the same thing, right? That means you have enough sample. If you have enough sample, then yes, you can approximate the true function very easily. But what if you do not have enough sample? Here's what I'm going to show you. Okay. What if you do not have enough sample, and the word enough sample, it has to do with like how fast the function is moving. So let me change exactly one thing. Psi 100x, and I'm not going to show you Lagrange yet. I need this, I need this, I need that. Okay. Okay. So here's what happens. Blah, 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 blah. Okay. So here's what happens. Okay. Let's consider a function of psi 100x, right? Psi 100x is a psi, except the frequency is much, much faster. This is the real function. Okay. So now, if you take only 11 points, right? Only 11 points. And let me put in some alpha. Okay. And then if you take only 11 points from all these functions, so think about this. The reason that we can reconstruct the sine function before is because we actually have multiple sampling when it goes up and down, right? But for this one, the function is much faster moving than we thought, right? The function is the red line behind. It's go up and down really quickly, but you're sampling only 11 times. Even though it crossed zero about 10,000 times, you're only sampling 11 times. And then you get this. And let's look at what happens when you do Lagrange to this point, right? I think it's quite clear to you that you're not going to get back the original line. The original red line is not going to happen, right? So I want to point out to you that this only works if you have enough sampling. Wait, what? 2.10. Oh, even 10,000 something is not enough. Oh, there. Just wait 2 seconds. Okay, you can see that the original function is the red line, and the Lagrange polynomial is the blue line. They are nothing close. Okay, and there is a problem with sampling because you do not have enough sampling for you to reconstruct the whole thing. Okay, so Lagrange polynomial only works if you have enough sampling, and there is actually mathematical proof on what exactly do I mean by enough sampling in the lecture note, which is very mathy, which you don't really care. But if you think about it, it does what we needed to do, right? It passed through every single point exactly. Right? It passed through all the 11 points, but whether it looks like the original function or not, no, completely not. Okay, so far so good. Right, that's what I want to point out, that it has to do with sampling as well. Okay, but for this one, for slow moving function, okay, you can guess it really easily. But you know, there are a whole bunch of other functions, right, that does exactly this. So keep that in mind as well, that we are doing interpolating. We are not just, we are not exactly getting the truth. It has to do with how fast the function is moving. Okay, so far so good. So that's one thing for today. Okay, that's about interpolation. Any questions though? Any question? Any question? Okay. There are other types of interpolation as well, which you can read when you need it, but typically the one that you need is in NumPy somewhere somehow. Okay, so it has about the same idea, that it tries to pass through all the functions. Sometimes you constrain it a bit differently and so on, but it's the same idea. Okay, so the next thing that I want to teach you today is how to teach the computer to do integration. Okay, last time, let me switch back to my thing. Let me switch back to my thing. Blah, blah, blah. That's not obvious. Obvious is here. Okay, so let's learn how to get the computer to do numerical integration. Okay, you know, integration is like much harder than taking derivative. It's much harder than taking derivative, but numerical one, that's easy. Right, you learn with Ajahn Jinda that you need a lot of tricks like partial fraction, integrate, bypass, and whatnot. Right, but differentiate, you need a couple of simple rules, right? Like the fact that you have a chain rule, you have a product rule, then you can do it. But integration is much harder. So let's start with something you can do by hands, so you can test. Okay, so if I ask you to integrate this dx, okay, you're gonna say, okay, Ajahn, that's easy, I learned it from Ajahn Jinda, she taught me so well. So it's gonna be x to the fourth over 4 plus c. That's not what we're gonna do. This is called it. It has a name, except I forgot the one that doesn't have the limit. What we are trying to do here is the one with the limit. Okay, so for example, if you try to integrate it with the limit like x equal to 1 and x equal to 3, then yes, what you're gonna get is x to the fourth over 4 and plug in 3, plug in 1, and whatever number you get. Right? So that's good. So these are, but at the end you're gonna get some number. Actually, let me get the number real quick. 3 to the 4 over 4 minus 1 over 4. Yes, 20. Really? Oh, 20. Okay. So these are the type of things that we want the computer to do, because it's very good at doing the numerical, right? So we want to get from the thing on the left to the thing on the right. So that means the thing that you need to specify are 3 things, right? The function that you need to integrate, right? The function that you need to integrate. So you need the function that you need to integrate. You need the limit, the lower limit. and the upper limit. Right? You need to think, and it should split, it should give me 20. That's good. There are some packages that do symbolic integration as well, but that's not the story for this class. Maybe for Ajahn Kanak's class though, not my class. It's hard. The thing is that it's hard. Okay, so let's think about how we would do one. Anyone has a good idea though? If I try to integrate x cubed, what would you do? Teach a computer how to integrate x cubed without giving it the rule that's x to the 4 or 4. What would you do? So x cubed look like this, right? This is y and this is x. From 1 to 3. So this is 1 and this is 3. What would you do? What would you do? Anyone has a good idea? Think about what physically, what exactly does it mean physically to integrate something from 1 to 3? What are you trying to find physically? Right, you're trying to find the area, right? You're trying to find the area. So how do you find the area? How do you find the area then? Anyone has a good idea? How do you find the area? You know the value of the function, like almost everywhere. You have the function to evaluate it. How do you find the area though? What did you learn in calculus 1 or whatever? Integrate the function. That's exactly what we want to solve, right? And that's exactly what we want to teach the computer to do. But tell me, how do you find the area? Which means it's the same thing as the question of how to integrate the function. How do you find the area? Like physically, like the dumbest answer there is. Okay, not bad, right? Not bad. Tanawin said, okay, Ajahn, this actually looks like a trapezoid for me. Maybe I'm gonna do a trapezoid. Yeah, that's actually not a bad idea. Not what Tanawin was suggesting. Right? Ajahn, this thing is really close to trapezoid. But then someone's gonna scream, Ajahn, but what if the function looks like this? What if the function is not that friendly like that? What if the function has a lot of going up and down? Then trapezoid might not be the best idea, right? What would you do? What would you do in this case? Create a new function. Riemann sum. Okay, good. You know the keyword. Riemann sum. What exactly does it do? Can you tell me? What exactly does it do? Riemann sum. What exactly does it do? What exactly does it sum up? Riemann sum. That's actually what I want. But what does it mean? Do you remember? Rectangle. Good. But we're going to do something better than rectangles because I want to show you something later that is you don't want to do rectangle. Rectangle is a stupid idea. Right? So you're gonna chop this thing up into a whole bunch of trapezoids. Are we good? Right? The smaller the trapezoid, the closer it is to the real function. Right? The goal, chop it up. Okay, and add up the area of trapezoid. This is actually Riemann sum, but a little bit more fancy. Okay, everyone understand the idea, right? And also we learned that if the trapezoid here, right, is really thin, we should get an accurate answer. If we approximate this with like not a very good trapezoid, with like 2 trapezoid, with like only this and that, you're gonna get a lousy area, right? Right? You think that more pieces you add, right? This is the theme. You add more effort by adding more pieces, by chop this thing up into more pieces, then we should get a better answer. That's our goal. Okay. Any questions so far though? Before we are going to do exactly this. Okay. Any questions so far though? Right? So we turn trapezoid, no, we turn the integral problem into the problem of just adding up the areas, which the area we know how to add. Okay, so let's do this. Okay, so let's look at one of the trapezoid pieces first. Let's look at the one trapezoid. So let's call this x0. Let's call this xl, lower limit, and this is xu. Okay, right? So we're gonna call the space between each of the piece. Oops. We are going to call the space between each of the piece h. So that means this thing gonna be xl plus h, right? And then the next piece is going to be xl plus 2h, and so on. You get the idea? Yeah. So let's consider this. Let's consider this triangle. Not triangle. Let's consider this trapezoid. Okay. How do I find the area of each trapezoid? Actually, let me just call it xi. That's easier. This is xi. This is xi plus 1. Okay. So how do I find the area of this trapezoid though? What do I need to know? That little piece. If I want to find the area, what do I need to know? What do I need to know? If I want to find the area of that trapezoid, what do I need to know? Anyone? Help me. Right, you need to know the height, right? You need to know the height. Which you know the height over here is going to be f of xi plus 1, right? And the height over here is going to be f of xi, right? So now the rest is easy, right? So that means the area of this thing is a half times the sum of the two sides, right? And multiplied by the width, multiplied by h, multiplied by f of xi plus f of xi plus 1. Okay, everyone good? That's only one piece. That's only one piece. We just want to add up all the pieces. So that's good, right? Right, it's just the area of trapezoid, nothing fancy yet. Okay. Now let's add up all the pieces, right? So let me name. So this thing is going to be x0. So that way it's easy to find, right? X0, okay, so xi is going to be x0 plus I times h. Okay. So that's good, right? And we need to be a little bit careful with the limit. Let me get this. So xu here, I'm going to call it xn. Let's call that xn. Okay. So let me ask you, how many pieces there are if there are n over here? N or n plus 1 or n minus 1? Can you tell me? How many pieces are there? How many trapezoids are there? N or n, there are three choices, n minus 1 and n plus 1. How many are there? When you think about problem like this in abstract way, right? This is what you should do. If I end with x1, then I have one piece. If I end with x2, right, then I'm going to have two pieces. So if I end with xn, then I'm going to have n pieces by, like, not mathematical induction, but by induction. You do three examples. I just told you not to prove it by example, but it's a good thing to do by example. Okay. So you can eliminate the choice really quickly. If I have one, I have exactly one trapezoid to add up. Okay, so let's do that. Let's do that. Okay, so I'm gonna add this thing up, right? Starting from x0. Okay, that's why I call it x0. If I start at x1, then you're gonna have some other trouble. Okay, so we're gonna add up all the trapezoid, which means the total area, which is the integral we want, right, is going to start from a half times h times f x0 plus f x1, right? That's the first piece. And then the second piece look exactly the same, f x1 plus f x2. Actually, let me draw you a picture so you can see how it works. So this is the first piece, x0, x1, right? That thing goes here. And the second piece, x2, that thing goes here. Okay, that's why x1 is repeated. And then plus 1/2 times h times f x2 plus f x3 and plus dot 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 plus a half times h times f xn minus 1 plus f xn. Okay, so we are not doing anything fancy yet, right? All we do is just add them up. Can anyone help me simplify? Help me simplify. What can I factor out? What can I factor out? A half h, right? So it's a half times h. So what's left over? How many fx0? That's one, right? From here. Fx0, there's only one. But all the other f except fxn, there are two of them, right? So that means you add up, this thing is a sum of 2 times f of xi. But we need to be a little bit careful. I from 1 to n minus 1, right? Because that n doesn't get repeated as well. And then add in the last piece, which is f of xn. Okay, so far so good. So far so good. And this is called trapezoid rule. Okay, so this means integral from x0 to xn of fx dx is just that guy. Okay, and you can see that we can adjust our effort here. This is the effort, right? The effort is like how finely chop you do to the function. The more pieces, the better. And we're gonna learn how much better it is. But first, let's implement this. Trapezoid rule should be like one line. Okay, so what I want you to do is the same thing, right? Integral of x cubed, but now you do it with this numerically. Okay, so let's go back to my notebook. Go back to my notebook. Okay, so trapezoid rule, you should try something like this. Trap f and then the lower, right? x0 and xn and n pieces. So this is a function and this is a flow. And this thing is an integer. Okay. Give me the area. right? You just write exactly the sum on the lower right corner, the sum. Wait, why is it on top? Yeah, so you just write the sum over here. Be careful about the first and the last piece, that's all. Right? And h, the way you find it, because you know that xn is the last one is x0 plus nh, so you can revert the equation and so on to figure out what is h. Okay, let's do that real quick. So h would be what? No, because we divide them into many pieces, right? Let's say you divide them into 100 pieces. H is going to be that number divided by 100. Oh, by n, not by h. Okay, now these three lines, you just taught computer how to do integral. I assume there's no bug. Okay, and we can do this with like, let's make sure with 1,000 pieces. 1 to 3, right? And let's say 1,000 pieces. Why is it 10? Because I forgot to multiply that by 2. There, really close, right? That's actually a convergence, which we're gonna touch on it right after this. So I want you to experiment with the number of pieces, right? You can go to the extreme. You can try 1, which is a terrible answer. You can try 100. You can try 1,000. Or even better, you can even plot, right? You can even plot this. Okay. Let me do something fun for you. Access is np.lin space 1 to 1,000. Say 1,000 piece. Wait, I cannot do that, right? Wait, let's call that range. List of range. So I made sure that they're all integers. 1 to 1,000. Do 1,001. Doesn't matter. Okay. And then what I'm gonna do is the error. This is not. This is like the actual error, right? You know it's gonna be 20. So let's take the absolute 20, the true answer, minus the trapezoid of f and 1 and 3 and n pieces. So let me put the code as n. But n in yes, that in a list. And then we can do something fun, like we can plot, like as we increase the number of p's, what happened to the error. And I should not start with 1. Let's start with 10. This is the log scale, so it went down really fast. So you can see the number of p's, it went down like much faster than linear, right? It's not like 1,000 times and it went down by a factor of 1,000. It went, if you put 1,000, like 10 times more effort, it should go down by a factor of 10. This is not linear. This is something much faster than linear, even though the algorithm is something really simple. Okay, which we're gonna see. But I hope everyone got this, right? Right. Got this. Let me push it as well. Right, this is exactly what we wrote, right? We transform the problem of integral into something that computer can do. Just add and multiply, nothing more fancy than that. Okay. Any questions so far though? Any questions so far? So let me try to convince you how fast, how good this thing is, even though the idea looks so simple. The idea looks really, really simple. It's actually the go-to method if you have no better idea. There are actually better method than this, but it's going to be slower and so on. Okay. So anything better than linear is good for us. Okay. Any questions so far though? Any questions so far? Any questions so far with trapezoid? Let me show you how good this thing is, even though the idea looks so simple. Okay. To understand how good this is, we're gonna go back to the very basic, like I told you last class, right? Everything in this class is essentially Taylor series. So let's imagine if you have only one piece, the only thing that you do, right? The only thing that you do is you try to extrapolate this linearly, right? You interpolate this linearly. That's what you're doing. Okay. You are interpolating this linearly, and then you integrate it, right? So linear interpolation, extrapolation, linear interpolation, then integrate. Okay, so we're gonna do exactly that. Okay, so let's just call this like x0. So this thing x0 plus h, right? Okay, so we're gonna do exactly that. Taylor series teaches the following, right? Taylor series teaches the following: f of x plus something. Let's call that c. F of x plus something, right? As an fx0. So the value of the function at fx0 plus by just a little bit, right? This thing is clearly fx 0, right? At least the first order is this guy, plus c times f prime at x0 plus c squared f prime at f double prime at x0 and a whole bunch of other things, right? Something on the order of c squared, c cubed. Right? This is a hand waving. The exact one is actually in the lecture note. The exact formulation, which requires something a lot more hardcore, is in the lecture notes. Okay. So let's look at this. This is what we are doing, right? We are interpolating it with a linear, right? So that means the only term that we use to do the integral is the first two terms, right? Only the linear one. Haven't get right? Only the linear one. That's what we are used to do. That what we used to do. Okay, because this thing is linear. This is our function, right? That blue line, this guy, are exactly the same thing. Okay, are exactly the same thing. And then we're gonna integrate this. Okay, so we're gonna integrate this. The integral that we want, right, is integral from c equal to 0 to c equal to h of f of x0 plus c dc, right? That's the area here. That's the area here, on the left, right? Okay. So on the right, we're gonna do the same thing. On the right, we're gonna do the same thing. So it is gonna be equal to f integral of fx0, right, plus c f prime of x0 dx dc, not dx, c equal to 0 to h, right? This is the blue part. This is this part. Let me highlight this. These two are our function, right? So this is essentially our trapezoid rule. You can actually simplify it. It's gonna become trapezoid rule, right? Because you are linearly extrapolating it, right, and then integrate. You can actually simplify this and get the trapezoid rule. Okay, but then we have the leftover. The leftover part is going to be integral from c equal to 0 to h of c square f double prime x0. Okay, c square f double prime x0, which you can integrate this, right? F double prime of x0, that's a constant that has nothing to do with c. So that means this thing is equal to the trapezoid. So the real integral. So that means the real integral. Okay, is trapezoid plus f double prime and something on the order of c cubed, right? This thing gives you like c cubed over 3. Everyone good? Right? Not c cubed, h cubed. Give you h cubed over 3. Okay. Is everyone with me so far though? Is everyone with me so far? So the goal here, what I'm trying to show here is that the integral, right? The one piece integral. The error is on the order of h cubed, right? Or you can think of, h is like 1 over n, right? H is like delta x over n. So this thing is like 1 over n cubed, which you may be really glad, right? Which you may be really happy. Okay, Ajahn, this is n cubed, much better than what we have. I was happy with 1 over n square, right? And n cubed, this actually means a lot, right? If your h is 10 to the minus 1, then the error is 10 to the minus 2. If your error is 10 to the minus 2, then your error is 10 to the minus 4. So your effort is like double, right? This is h. No, triple, not double. Minus 3, minus 6. So that's good. This is like 6-digit action. This is like crazy. Okay, so that's good, right? I want to show you very simple idea, right? Of trapezoid, it gives you a really good error. You can actually make something better, but from this, I think you can see how to make it better. To make it better, you just add more terms, right? You just do a better, you just do a better job at approximating the function by including the higher order. Okay, that is also in the homework, but except it's optional because it's actually quite algebraically tedious. Okay, you don't learn much more. There are algorithms that helps you do that as well. Okay, any questions so far or any question? So if you have one piece and this thing is h and then you integrate in a lousy way, then your error is order of h cubed. If you only include the first derivative, then the error is order of h cubed. Okay, but But you see, what we are doing is not just one piece. We sum up a whole bunch of pieces, right? We sum up a whole bunch of pieces. So here, this is exactly what we do, right? So we're gonna need, how many of this we're gonna need? So actually, let me write this. This is 1 over n cubed, right? So we do trapezoid n times, right? We do trapezoid. Actually, let me change the color. We change the color a little bit. We do trapezoid n time. Okay, so we do n times this. This is sort of hand waving. The actual proof is in the lecture notes though. But I want you to see that everything has to do with the Taylor series. In the lecture note, I did the Taylor series in a much more careful way. Okay, but it says exactly the same thing. Okay, so but the real integral, right? We add up a whole bunch of trapezoids. Okay, we add up a whole bunch of trapezoids. Right? We are not just doing one piece, but we're doing n pieces. Okay, so when we do that, the sad thing is your 1 over n cubed over here gonna get multiplied by n, right? So what you have is going to be more like, actually let me do this. What you have is going to be more like the following. Gonna be the real integral is the trapezoid sum. This now you do many pieces, right? Trapezoid sum. Okay, that n I just put it as a sum. Okay, but that O 1 over n cubed gonna become O 1 over n square. Order of 1 over n square. And fx0, that's kind of sketchy. It's actually some pieces. It's actually this guy. Okay, so that's good. But this is not bad. 1 over n square is good. 1 over n square, you should be happy with it. Okay, because like I said, if your pieces, your edge is 10 to the 1, right? Then your error is on the order of 10 to the minus 2, which is not bad. If you like 10 times, put 10 times more effort, 10 times more effort, because it's literally 10 times more effort because you sum up 10 times more terms, right? Then this thing is 10 to the minus 2, but your error goes down by 2 significant digits, right? If you put in like more, 10 more times, your error goes down by a factor of 100. Right? Then this thing is 10 to the minus 3. Then your error goes down by 10 to the minus 6, which is like perfect, which is perfect. Are we good? I think I convinced everyone, right, that the error needs to be on the order of 1 over n square, which I'm going to give you the exact formula here. The exact formula is, I don't remember it too. Blah, 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 blah. It has 1 over 12 somewhere over here. There. The exact formula is that 1 over 12. Times 16. So the exact formula, which I'm going to cheat because the proof, if you're interested, you can read the lecture note, but if you're not interested, just get the last line here. You can see it's order of 1 over n squared because there's 1 n squared over here. Okay, so the error from trapezoid is going to be 1 over 12. The bound cube, right? The bound cube, which is the left x0 of xn minus x0. Doesn't matter because you're going to take the absolute anyway. Over n square and f double prime c for some c in what in x0 to xn. Someone convinced, so at least I convinced you with the part with 1 over n square. And f double prime, I think I convinced you with 1 over n square and that part. But 1 over 12, you need to be a little bit careful to get 1 over 12. Okay. But all the other part, I think you're good. Right? So let's do some example. Let's do some example. Like what exactly do we expect? Right? If we look at the graph that we got, where is it? if you look at the graph that we got, this thing is actually 1 over n squared. And you can plot it right on top of each other. It's 1 over n squared. Okay, with some factor in front. Okay, this thing is 1 over n squared. So let's look at some example that I want you to be able to do. Okay. So for example, if I want to be able to calculate the bound on error of this guy, right? So I want to know the following. I want to know. So I want to know, how do I make this bigger? Okay, let's say I want to know that if I try to integrate x equal to 1 to x equals to 3 of x cubed dx. Okay, if I use trapezoid 100 times equal to trapezoid 100 piece. Okay, I want to know what is the bound on error, right? The bound on uncertainty plus or minus what, right? And we learned that this thing is essentially the formula that I gave you here, 1 over 12. And then the bound, let's say that the bound is called xn minus x0 cube divided by n squared times what? F double prime c. So sum c in xn to x0. Oops. X0 and xn. Okay, this equal sign is the actual equal sign, though. You can actually prove it. That's why you need 1 over 12 over here. Actual equal sign. But you've seen this before. You see the theme that even though you know that they are equal, there's one problem. You don't know what C is, right? So you can only bound the C, right? You can only be conservative with C. Okay, so here's what you need to do, right? To see what the error is, you do the following: 1 over 12 multiplied by 3 minus 1 cube divided by n square, which n is 100 square, multiplied by f double prime of z. Now we need to calculate f double prime and see like where it is the maximum, right? Where is this the largest? Okay, so f double prime of x is going to be 3 times 2x, right? And we let x to be from 1 to 3. So we know the largest value that this guy is going to attain is going to be at 3, right? This guy gets largest at 3. Largest, I mean absolute, it's going to be largest, but this time is positive, so we don't really care. Okay, this guy is going to be largest when x is 3. So that means we know that f double prime of z, whatever that c is, we can go find it, is going to be less than or equal to 3 times 2 times 3, where that last 3 come from there. Okay, which means we know that this thing going to be the absolute of this thing going to be less than, but it's positive, so we don't really care. 1 over 12, and that thing is 8 by 100 square multiplied by that thing, which is 9 times 2, which is 80. Everyone good on how we calculate the error term, which I'm not going to emphasize though, but you should see it one time that you can actually calculate it if you like. You should be able to, you should calculate it like 1 or 2 times in your life, and then, okay, there's a way to do it. And the next time that I need it, then I'm just going to look up Wikipedia and whatnot. Any questions so far though? Any questions so far? I think I convinced you that the error needs to be on the order of 1 over n squared. That's the part that I kind of want you to know. Even after this class, that trapezoid, even though it looks so simple, it's actually really fast. Okay. The next thing that, okay, you should be able to do, given the formula, you should be able to calculate the error term. So any questions though? Any question before we go and calculate it? Any question? Or I lost most of you already. You guys are awfully quiet. I know it's late in the evening. I know it's late in the evening. So let's do that together. Let's do the notebook together and we're gonna call it a day. Okay. Let's do the notebook. Uh, oh, okay. Okay. So bound on error, we can write a function to do it, right? If we are really lazy. Right? We have what? 1/12, right? 1/12 times 8. 8 comes from like 3 minus 1. Cube and then divide by 100 square. The first one was like how much? 1 square. Doesn't matter. It's 2 number 2. Number 2 is 100, right? So typically you don't go over 1,000 pieces. It's a waste of time. Unless you really want to, though. Unless you're running into some trouble, then you start doing something like more drastic. Okay. So the bound on error for 100 piece is this guy. Let's try this. Okay, 100 piece. Right, which is pretty close. So you are not sure about these 2 digits. That's all. Okay. So typically you don't need more than 1,000 piece in most applications, unless you want to go crazy. Okay. Any question? If not, let's look at this. I think that's quite clear. You just plug in the formula and figure out what it is, right? So next thing is, that x cube, there is really no point for you to integrate with trapezoid, right? Because you can do it in your mind really quickly and you get infinite accuracy because you do it analytically. Because there's no point for you to integrate x cube but with numerically. But this guy, you cannot do it by hands. If you can do it by hand, let me know immediately though. There might be some smart way to do it that I don't know. Okay. There might be some smart way that I don't know of. By smart, tonight you should Google this word. Okay, tonight you should Google this. Something called Gaussian integral. You should Google this. My mouse. Google something called Gaussian integral. You're gonna be mind blown. You can derive it easily. If you look at the answer, then you're gonna doubt yourself. Okay, let's do this. But this thing, oops, this thing you're not gonna do it yourself, right? It's like, oh, come on, Dan, this is so hard to integrate. You can try like for 5 minutes and then you gave up. Okay, but this thing is easy now, right? If you want to integrate this from 0 to 1, Dan, that's so easy. I can do this. Return exponential, right? Minus x multiplied by, oops, I think I need this. And multiplied by np dot sine x squared. You can try like by parts and whatever you want, but I think you're gonna get into a loop. Okay, and I just need to do this, and then my problem is done. There, done. You think it's much easier than like figuring out how to do integral by parts, right? Everyone can see, right? The power of this is when you get a function that you have no idea how to integrate. Okay, so far so good. This is one of the things that you don't want to do it by hand. But okay, of course, by now every one of you should know, right? There's a thing in the world called Wolfram Alpha that you can ask it to integrate. And behind the scene, it actually does something very similar. Integrate. Integrate. Okay. What was that? Exp minus x times sine x squared. Oops. Times sine x squared from x equals 0, dot 1, and then you press enter. Or maybe it will tell me how to do it analytically. There. See, that's simple, right, Adil? That's simple. It has to do with error function. Very simple. Right. Exactly. In the homework, you're gonna figure out what that ERF means. You look at this. Look at this. Not only that it has to do with error function, it has to do with complex number as well, right? Square root 4 of I, that's square root I. The fourth root of minus 1. See? And then you think, okay, Ajahn, how does it have something to do with pi? I don't know. I don't know, but most Gaussian integral has to do with. In the homework, you're gonna do ERF. We're gonna talk about the homework right after this. Okay. Okay, but you see, the power of this comes when you actually need to integrate something you have no idea how to do by hand. If you see like x cubed, don't bother integrate numerically. Just put x to the 4th over 4, and then you're done. That's much easier. But when you see this, do this. Do this. Don't bother do it by hands, right? And you know the weakness of this is because you don't have the plus c, right? You don't do it analytically. Okay. Okay, and number 6, I'm sure you can do it, right? So we learn, right, that the error. So for number 6, here's one question that sometimes you need to answer yourself, right? So for example, if I want integral of this, which you know how to do it analytically, that's why I pick it. So it's very easy for you to differentiate and figure it out. Okay, if I want the answer for this, right, such that it's like it's accurate up to like 6 digit, right? 10 to the minus 6. How many pieces do I need? Okay, so you can do the following, right? You can do it in reverse. You know that the error, right? Actually, let's do it in the most stupid way. You can actually like revert the equation, but let's today I'm lazy already. Multiply by like 0 minus 1, so that's 1 cube, right? 1 cube divide by n square, right? Multiply by f double prime. F double prime, you mean, you know, e to the minus x is e to the minus x, and you can differentiate it all you want. It's gonna be just be e to the minus x, and the largest value is 1, right? At when x is 0. Okay. Right now you have this. You can follow, right? But let's be more civilized. Let's be more civilized. Let's be more civilized. So for example, you know, this is what you need. You want 1 over 12 times 1 over n square, right? Times 1 over n square has to be less than or equal to 10 to the minus 6, then you can solve the rest. Right, then you can solve for n. You just put the n over here, 10 to the minus 6 over here, then square root everything. So that means okay, 1,000,000 10 to the 6 divided by 12. 10 to the 6 divided by 12 has to be less than or equal to n squared. So that means I just take the square root. What? Why don't you like me? Oh, because you need this. No? What do you need? Maybe you need this. And that there, whatever the number is. So it's gonna become NP the square root 1e6 divided by 12, which is about 300 pieces. Right, so that means you can just do this. You can just do np.exp minus x, and then you just need 300 pieces. 302. So let's make it 302. 1 from 0 to 1, blah, blah, blah. Invalid syntax, because I did that. And that's all. So you guarantee that it's accurate at least 6 digits, right? Which this thing is easy, right? You just integrate it. Everyone good so far though? Everyone good so far? Right. So 111 or 112? What is 1e/11 and 1e/12? One, I see. Should be 12. 288, okay. Doesn't change that much. You don't really need to be that accurate, right? You can go overboard a little bit. Okay, off by 1 or off by like 10, I don't mind. Okay. Does that sound good to everyone though? You learn 2 very important things. You can get computer to do like more cool stuff like interpolation and integration. In the homework, I think it's something fun this week, but I don't remember what it is. Let me get the homework for you. Remember, please hand in the homework. Please do the homework. Whether you hand it in, that's another question, but please do the homework. That's more important than handing it in. Okay, so okay. Let me clone the thing. It doesn't like the integral. 2 seconds. Let me clone homework 3 really quick. Copy. No one posted the Luigi. Didn't you guys do it? Anyone succeed in getting Luigi? No one? You guys should do it. It's fun. Uh, okay, let me brief you on what the homeworks are doing. So please catch up on the homework. It's very important. Okay. So the first 2 questions are like whatever you copy from the exercise to the homework, right? Okay. So for this one, you probably don't want to do it by hands. I think this one you can do it by hands with the partial fraction and whatnot. You might be, I don't know. X squared, sine x squared is notoriously hard. Okay, so, but in the homework, you're gonna learn something very important too, that, right? The trapezoid that we did, we sum up all the function, right? We sum up all the function, but there's a problem here, that what if I want to integrate up to infinite? So that is this guy. Doesn't exist anymore, okay. Probably they don't like me anymore. So just look at ERF table. This is the C-score table that you learn in statistics. But here, now you're gonna figure out how to get this table. Where's the C table? No. ERF. You know what I'm talking about, right? For those of you who take statistics already. Give a second. There. You're gonna figure out how to get this table. Okay, because you know that there's one little problem with this table, that you need to integrate from x to infinity, and if you try to sum up to infinity, okay, it's not going to work because you try to sum up to infinity. So one trick people do is this. Okay, just read. It's long, but it's like 3 lines. It's long, but it's 3 lines. The code is 3 lines, but it's long because I teach you how to work around the infinities. Okay, And then you're gonna learn how to do the following. This thing is to get you figure out how to combine the tools you learn, right? So all I am asking is to find the position for the red line such that the area here is exactly whatever number that I give, 4.0, to find exactly the value of x over here, such that the value is 4.0. Okay, you gotta go figure out how to do it. It's like, I don't know, 10 lines, but you need to figure out for like half a day or something. Okay, this is why you need to write some code, probably 100 or 200, or maybe less than that if you know what to do. Okay, you're gonna learn about something called Fourier series. Okay, it's very close to Taylor series, except it's called Fourier because it claims that every periodic function you can approximate it with a whole bunch of sine and cosine. And I tell you exactly on how to find all the coefficients. Right. So every single function can be write as a sum of sine, cosine, and I tell you exactly on how to find a and b's. If you're interested on why a and b looks like this, then Wikipedia or YouTube help you. Okay, it has to do with orthogonality and so on. Okay, and then you're gonna find the series for a whole bunch of things. Okay, and number 6 is a really cool problem. It's a really cool problem because once you learn discrete math, right, you learn sum of I is like n squared polynomial of degree 2. Sum of I to the second is polynomial of degree 3. Sum of I cubed is polynomial of degree 4, which you can believe that it has to be that way, right? The goal is to figure out what is I to the any number k, because you know it's going to be a polynomial of degree k minus 1, or k plus 1. Polynomial of degree k plus 1, right? Which means you can use Lagrange polynomial to actually figure out what are all the coefficients, right? What is this 103, 102, and 106? You can figure out all the coefficients. Once you figure this out, it's going to be really cool. Okay. So use Lagrange polynomial to do this. So any questions so far though? Try to get every homework by next week, if possible. 1, 2, 3. The goal is the homework should be weekly, but I don't mind for you to be late by like 1 week or so. But by now, not many people hand in homework once, so please do so. Otherwise, you're gonna find the exam pretty hard. Okay. Any questions so far though for today? Try to do the homework weekly. Okay. If it's late by a week, then I'm good. Any questions though? Any question? Like last sub question. Okay, so the thing is, don't struggle alone. Don't struggle alone. Is not fun. Struggle with your friend. Okay. Struggle with your friend. So scream on Discord, then someone's gonna come and help you. That's the best place to do. If you try to message me privately, sometimes I don't get to answer it. But if you do it in the public room, then someone's gonna come and help you before I do. Yeah, so that's the place where you get much faster answer. Okay, so any question though, any question? If not, we're gonna call it a day and see you next week. Okay, bye everyone.